subtraction might or might not be commutative depends on the underlying set, meaning you can't sort of give a general description as to why subtraction isn't commutative by simply saying it's not. Show me that it's not by handing me two integers, 2 and 3 or 7 and 18, I don't really care, and convince me that if you do 7 minus 18, it's the same as 18 minus 7. Now if that seems a little bit weak, I mean a good example might be convince me that matrix multiplication is not commutative. Folks, sometimes matrix multiplication is commutative. Depends on the underlying set. Heck, if you look at those 4 matrices that we've looked at inside the 2 by 2 matrices over the reals, the ones with plus or minus 1 on the main diagonal and zeros everywhere else, there's a set of matrices, and multiplication on that set is commutative. So if you're going to convince me matrix multiplication isn't commutative in general, you actually have to write down some specific examples where things fail. Okay, a second comment on that first homework assignment. Yeah, what some of you failed to do both in this assignment and on the second assignment was keep your eye on the prize. You're handed a set and an operation and you're asked whether or not the set together with the operation forms a group or maybe forms a subgroup of the given group. And in most of the situations, what you're asked to do is show that whatever it is that describes the set in question, maybe the set is the set of even numbers, maybe the set is the set of upper triangular n by n matrices having no non-zero entries on the main diagonal. Maybe the set is the collection of functions that pass through the point 1, 0 with blah, blah, blah. Whatever the set is, the prizes are always convince me that if you start with two things in the set and you combine them, that the result's back in the set. That's closure. Convince me that whatever the identity element is in the set. In other words, has the right property. Convince me that if you start with something in the set, i.e. has the right property, that its inverse also has the right property. And what some of you were doing was sort of either not fighting the battle at all or sort of fighting the battle halfway. For example, this goes for both question... the even integer question, and it also goes for the upper triangular no non-zero values on the main diagonal, and it also goes for the functions question. You'll say something like, pick two things in the set, maybe the set is the even numbers, show that when you add them together the result's even. Okay, that's fine. But why? Why is the sum of two even integers even? Some of you just said, well, the set is closed because the even numbers are closed. That doesn't tell me anything. Why? Because if you take two even numbers, one of them looks like 2 times x, and one of them looks like 2 times y. That's what it means to be an even number. You can write it as a multiple of 2. And if you add them together, you get 2x plus 2y, which is 2 times the quantity x plus y, which is of the correct form. It's 2 times an integer. Check. You might say, well, you're being too picky. I'm not being too picky. Heck, I mean, if the set was the set of odd integers, why is that any different than the even integers? Well, that set's not closed. Similarly, a lot of you just said, well, the identity element is in the set 2z. Yeah, it is, but why? Not that just you have to check that it is. You have to convince me that it is. Why is 0 an even number? Because you can write 0 as 2 times an integer. It happens to be that you can write 0 as 2 times 0. Why can you write the negative of an even integer as an even integer? Because negative 2 times an integer is 2 times negative that integer, which is the correct form. So keep your eye on the form. More words about that. So for example, in the second assignment, when you were asked to show that the set of n by n upper triangular matrices having no zeros on the main diagonal is a group. What some of you said was, well, if I take two things in that set and I multiply them, I get another n by n matrix. I'm done. You're not done. Okay, you get another n by n matrix. That's good. But you have to make sure that the result is in the set. You have to make sure that the result is an n by n matrix that's upper triangular, because that's what it means to be in the set, and that has no non-zero entries on the main diagonal. You have to check everything. You have to check that the identity matrix not just exists, of course it exists. You have to convince me the identity matrix is an n by n matrix that's upper triangular, that has no non-zero entries on the main diagonal. Well, yeah, it is, because it has all ones on the main diagonal and there's nothing below the main. So I'm not sure how to reinforce the necessity of, when you're showing something as a group, always looking back explicitly at what the property is that puts something in the set or in the subset, and making sure that each of the three things has the right property. Either the product of two things in the set, or the identity element of the group, or the inverse of something that's already known in the set. And I don't know, maybe you might want to just in big bold letters. Here's what this set consists of. 3 properties. N by N, upper triangular, no non-zeros on the main diagonal. And then in each step, you got to convince yourself that's what's going to happen. All right. Some remarks about the function question. I think this was numbers 15 and 16 in section, was it section 4 or section 5? I forget. Number 16 and number 15. Let's look at number 16. That one was a little bit more interesting. Section 5. You're looking at this thing called F tilde is what? It's the F from the reals to the reals where f of x not equal to 0 for all x. Right? So that's what F tilde was. And then you're looking at a subset of it. I forget what the name of the subset was. Let's just call it S. S is the elements in F tilde. G in F tilde with the property that G of 1 is 1. How did I do here? I get the number right? I think so. Okay. And the request is to show or disprove that when you look at this subset, that you get a subgroup of this where the operation here is multiplication. All right. Well, let's start first by looking at what the heck these things are. The elements of the set are elements of this bigger set, of this thing that you're told is a group. The things in the big set are functions. They're functions with the property that the domain of the function is the reals, what comes out is in the reals, and you're told that any function in the set has the property that regardless of what value you plug in, you never get 0 out. Okay. And then what you're asked to do is look at the subset of those things. Well, they're, again, functions with the property that when you happen to plug in the number 1, that the value 1 comes out. And so what I asked you to do as a first step here is give me some sort of pictorial representation of what the elements of this set look like. And let's see, did they actually give a name to this set, or they just said, here's a set? Okay, let's just call it S. It'll be a little. So, folks, what does it mean? What does it mean to say that you've got a function where when you plug in 1, that 1 comes out?
The thing goes through 1, 1.
The thing goes through 1, 1. So can you draw some pictures of some of those? Sure, here's one. That's a good one. And here's one. That's a good one. Well, I've got to make sure, though, that f of x is not 0. So I've got to make sure that whatever I draw here doesn't cross the x-axis. For what it's worth, a couple of you said, well, therefore it has to be a positive function. Well, you're not told that the functions you're interested in are continuous, simply that they're not 0. So technically, here's a valid choice. And there's an example. Goes through. There's a lot of other choices. Okay. Heck, here's one. In fact, let me put this in a little more boldly. Here's a function that goes through 1, 1. Okay, now, question is this subset actually subgroup? Well, what do you got to do? You got to make sure that when you take two things in here and you do whatever the operation is, that you get a result that's in there. So what do you have to do? You have to take two things in there. What are the things in this set? They're functions. So you have to take two functions. What do you want to call them? How about f1 and f2? So pick two functions in the set. Show that when you do the operation, and the operation is simply function multiplication, what does it mean to be an S? It means that when you plug in 1, that you get 1 out. So how do you do that? Plug in 1. What do you get? Well, folks, what does it mean to multiply two functions together? It means you just plug it in. Definition of functions. f1 times f2. That's what it means to multiply, x squared times sine x. It means you take the x squared function, multiply it by the sine x function, and if you're handed an input, you drop it into each one, you multiply. Oh, but let's see, what does it mean to say f1 is an s? It means that that first thing is 1 and the second thing is 1, and you get 1. So look, I've plugged 1 into the product and I got 1 out, so check, closure. I mean, I'd ask for another sentence here telling me what you just did, but that's the computation you need to do. Second, is the identity element in the subset? Well, what is the identity element? Under function multiplication, here's the identity element, I just drew it. Some of you said that the identity element is the number 1. The identity element's not the number 1. It's the function e having the property that e of x is 1 for all x. That's the identity. Because this is the function that has the property that when you combine it with any other function, it doesn't change the other function. So there's the identity function. Question, is it in the subset? It happens to be in the subset because it happens to go through the right point. Or rephrased, it happens to be in the subset because when you happen to plug in the particular input 1, then 1 comes out. 1 comes out for everything. But you've got to convince me that this function is in the subset. You have to convince me that when you plug 1 in, that 1 comes out. Well, it does. Okay, so e of 1 is 1. Check. And the last one is, all right, if you hand me an element, its inverse exists. Why? That's where this condition gets used, folks. If I hand you a function and it would have gone through the x-axis here, then there would have been a place where the output was 0, and you wouldn't have been able to write down an inverse function for it. So the fact that the inverse exists is a consequence of the hypothesis on the functions that we're looking at in here. But then once you've got that, it turns out then that f inverse is just 1 over f of x because the operation here is multiplication. Now plug 1 into the inverse, 1 over f of. All right. So that's what's going on. And it's, again, just a matter of keeping your eyes on the prize, figuring out what the heck the things are that you're working with, and then secondly, deciding what property those things have to have in order that they actually land in the corresponding set or subset. All right. Last comment on the homework. And no, 2 last comments. They're both stylistic. What a lot of you are doing, and quite honestly, I see this a lot from students early in the semester, the Math 414 course, is you're writing down lots of facts, most of which are true, but a lot of which are completely not germane to what you're trying to do. And if you say, well, I haven't told you anything wrong, yeah, I agree with that, but it's like writing an essay about George Washington and just throwing stuff in about John Kennedy. Well, okay, you might be telling me true facts, but it's just not of interest to me. So please, stylistically, go back through your proofs and make sure that all the statements that you're putting in are really of interest. On some of your homework I wrote, not of interest or not germane or so what or something like that. Okay, it's true. I can't put an X through it because you haven't told me anything wrong, but you sort of started randomly pulling facts out, and that's typically not a good thing to do. Second stylistic comment is a couple of you wanted to do some proofs by contradiction here. Yeah, okay, that's fine. For instance, in the one, show that there's only one idempotent in a group or something. I would suggest stylistically, anytime you do a proof by contradiction, read back through your proof and ask whether or not it could have been done just as easily by a direct proof. Some of you, for instance, for that idempotent question said, suppose there were 2 idempotents, I don't know, F and G or something like that. Show that F equals G. Or suppose that there's 2 distinct idempotents, let's get to a contradiction, and in the end what you wind up proving basically is that if you have an idempotent, it is the identity, which is the goal, rather than a proof by contradiction. So it's just, again, I offer that as a stylistic comment. And finally, this is more than a stylistic comment. On the question that asked if you start with an abelian group and you look at the elements inside the group that have the property that when you square you get the identity, 47 it was, some of you got sucked into the trap, and the trap is that you prove that result without using one of the hypotheses of the question. The question is, if G is an abelian group, show that blah, 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 blah. And I can't strongly enough suggest that once you're done writing your proof down, you should always go back through your proof and make sure that somewhere in your proof you've used every one of the hypotheses in the question that you've been handed. Because some of you wrote down proofs and never used the fact that the group was abelian, and folks, it turns out that the statement is false if you're looking inside a non-abelian group. So if you've proved something and you haven't used all the hypotheses in the given question, I mean, maybe you've found a hidden secret to this question or something, or maybe you've done something incorrect, and unfortunately the latter is probably what happened here. Okay. All right. So again, I'll try to post homework solutions by tomorrow, but definitely by Friday, and we can move on from there. All right. All right. So, folks, if you have any strong comments one way or the other about having filled in Monday's class by doing a pre-recorded video, let me know. If you really liked it, I might do it again once or twice in the semester. I don't really like to do it on a regular basis, but if it works for you, then if there's a day where I have to maybe be out of town again or something, I can do that. Or if you really hated it and said, my machine gagged on it, or I couldn't find time to do it, or whatever it was, that's fine. It can't be real. Well, maybe not. Okay. So here is what I'll say we did on Monday. Here's what I did on Sunday, and you viewed between Sunday and now. What we're going to look at is a new type of groups. So new groups. These are what are called permutation groups. Permutation groups. And the notation is, let's see if we can find some pens that work a little bit better. At least I got some today. The idea is hand me a set, and it doesn't really matter what the underlying set is, so that we typically choose the set and denote it the numbers 1 through n. Then S sub n is the set, but we showed in the video on Monday, is the group of permutations of the underlying set 1, 2, up through n. Okay. We showed it's a group. We actually noted, just by a discrete math result, how many elements are in this group. There's always n factorial elements. So what we've now done is we've written down a group that has, let's see, if n is 1, sort of an interesting group. So we'll typically assume n is bigger than or equal to 2. Even n equals 2 gives sort of an uninteresting group. If you hand me the permutations of a set with 2 elements, well, there's only the identity element and the switch, so there's only 2 elements in there, and that's sort of not too interesting. But once n is bigger than or equal to 3, these become really interesting. For instance, S sub 3, the permutation group with 3 elements, or on a set of 3 elements, has 6 members in that group, because 3 factorial is 6. If you look at the group of permutations on the set 1 through 4, you get a group with 24 elements. If you look at the group of permutations of the set 1 through 5, you get 120 elements, etc. Each of these folks are different groups, but they sort of are part of the same family, so we typically define all of them at once rather than saying here's what S3 is, and here's what S4 is, and here's what S5 is, etc. So what this has done for us is, for the first time, allowed us to write down finite groups, groups with finitely many elements, that are not abelian. Because what we showed in the video is that if n is bigger than or equal to 3, that you can always find at least 2 permutations, so that if you do the permutations in one order, and then you switch the order, that the outcomes are different. All right. What we did at the end of that video was to start writing down some ideas corresponding to permutations, and I'll remind you of those briefly, and then we'll look at some concepts associated with these permutations. We'll look at certain types of subgroups of these permutation groups, and then if we have time at the end, talk about some actually relatively deep results regarding some specific subgroups of these permutation groups. Okay, so the idea was if you pick something in here and the typical notation for permutations are Greek letters. Typically the letters sigma or tau or kappa are used. So if I pick something in, let me make up a sort of easier example. I'll start from scratch here, make another. Maybe sigma is, well, remember how we can describe what permutations are. We simply list out what all the possible input values are, and because I've asked you to look at S sub 7, maybe this particular permutation looks like this. 1 goes to 2, 4, 1, 3, 5, 7, 6. So this means, for example, sigma of 1 is 2, sigma of 3 is 3, sigma of 6 is 7, etc. And what we were looking at the end of Monday, at the end of the video, was the notion of the orbit and the intuition is, if you hand me a permutation, you can think about the underlying elements of the set, here 1 through 7, as being sort of chunked into subsets. And the way you chunk them into subsets is by simply starting with whatever element you'd like in the underlying set and sort of following through what happens to that element under the permutation. So that here, for example, if I start with 1, when you run it through the permutation sigma, becomes 2. In turn, 2 becomes 4. And in turn, 4 becomes 1. And once you get back to where you started, we're going to call this a cycle or an orbit corresponding to the element 1. So we get this subset, 1, 2, and 4. Notice it doesn't really matter where you start. If you had started with 2, you could have played the same game. 2 goes to 4, 4 goes to 1, 1 goes back to 2. So once you've got this, it sort of cycles through. What other orbits do we have? Let's see, 3. Well, 3 stays at 3, so that's sort of uninteresting. 4, I've already analyzed what happens to 4. It goes to 1 and then to 2. 5 stays at 5. That's uninteresting. 6 goes to 7, which in turn goes back to 6. So here's another orbit. 6 and 7. Now, technically, the number 3 itself is its own orbit because it doesn't get moved by sigma. So we're not going to really be interested in the effect of sigma on 3 just because there is no effect of sigma on 3. It stays at 3. All right. Now here's the idea. Turns out, proposition. Now let me give you a definition first. Definition. A cycle is a permutation, a special type of permutation having just one, only one non-trivial orbit. Yeah, this is a trivial orbit. Just 3 sitting by itself. It's no big deal. 5 sitting by itself. So let's see. Is sigma a cycle? No, because sigma somehow consists of 2 non-trivial orbits. It has this orbit and this orbit associated with it. Let me give you an example of a permutation that is a cycle. Example, tau is, and let me indicate where it is, in S7. Tau is this permutation, 1, 2, 2, 4, 3, 3, 4, 1, 5, 5. Here's another, I haven't indicated that this is a cycle yet, but you'll see in a minute why it is. Kappa is the permutation of the numbers from 1 to 7 that you get by doing 1 to 1, 2 to 2, 3 to 3, 4 to 4, 4 to 4, 5 to 5, 6 to 7, and 7 to 6. All right, let's see. Let's write out the orbits of these 2 permutations. Well, for tau, 1 goes to 2, 2 goes to 4, and 4 goes back to 1. So I've found one orbit. It involves 1, 2, and 4. Yeah, but look at everything else. Just stays fixed. If I don't look at 1, 2, and 4 and look at everything else, 3, 5, 6, and 7 remain. So the other orbits are trivial. So this particular permutation has only one non-trivial orbit, so it is what we call a cycle. So tau is a cycle. Similarly, let's see, what can I say about kappa? 1, 2, 3, 4, and 5 stay the same, so the only orbit here is 6 to 7 back to 6. So here's the only orbit, non-trivial orbit, of kappa, and kappa is then a cycle. Now hopefully it's somewhat clear what I've just done. I've in effect taken this thing called sigma, which isn't a cycle, and I've sort of parsed it into two pieces. The piece that corresponds to this first orbit, where I do what the orbit corresponding to sigma did, but then I leave everything else alone, 6 to 6 and 7 to 7. And similarly, I then take the other orbit, I do the action or whatever it was that sigma was doing on those two things, and leave everything else alone. Note, for the three permutations that I just wrote down, sigma is tau circle kappa. Why is that? Well, what I'm claiming is, regardless of which of the numbers 1 through 7 I run through the function, I can either just run it through sigma directly, or I could run it through first kappa, then tau. Well, yeah, if I hand you the number 1, for example, running the number 1 through kappa doesn't change it. And then it does whatever tau does, which of course is the same thing that sigma did to it. How about 2? Yeah, if I run 2 through kappa, it doesn't change it, but then 2 goes to 4. 3. No, 3 doesn't get changed at all. 4, 5, 6. Let's try 6. If I run 6 through kappa, 6 goes to 7. But then 7, when I run it through tau, remains fixed. So 6 goes to 7. That's exactly what sigma did to 6. Took 6 to 7. So here's going to be the idea. If you hand me a permutation and you break it down in its orbits this way, and for each orbit you simply do the permutation that corresponds to the cycle that gets generated, then you can write any permutation as a composition of cycles. Now let me give you a little bit more verbiage before I write that down. It turns out in this particular case, for these two particular permutations, I'm certainly not claiming that I can do this in general, it turns out you can switch the order. And the reason that you can switch the order is the things that tau moves, 1, 2, and 4, and the things that kappa moves, 6 and 7, are disjoint. So what we typically do is we call these disjoint cycles, and I'll write this down in a minute. The statement is that in general, cycles don't commute. In other words, if I hand you a cycle and I hand you a cycle, and I ask you to compose them, doing them in this order might be completely different than if you do them in this order. But if you have cycles that are disjoint, where the things that they're affecting are disjoint in the underlying subset, then they will commute. Okay. So here then is the results. I won't prove it for you, but the punchline is that in effect I've given you enough information in this example to allow you to piece things apart appropriately. Proposition 1. Any two disjoint cycles commute. Meaning, if you hand me any two cycles and the underlying set elements that are affected by those cycles are disjoint, as they were here, then in fact it doesn't matter which order you write them in. Be careful here, folks. This does not say that any two cycles commute. It says that any two disjoint cycles commute. And I'll show you in a minute a situation where even if I give you cycles, if they're not disjoint, then they might actually...
One more time.
Please. Disjoint, Richard, means this, that when you look at the orbits that they affect, if you look at the one non-trivial orbit, let's see, the things that were included in the one non-trivial orbit here are the elements 1, 2, and 4. The things that were included in the non-trivial element here are 6 and 7, and these two sets have no overlap. The intersection of these two sets is empty. That's the word disjoint. Okay? Yeah, so the word disjoint means that the intersection of the orbit elements here and the orbit elements here is empty. Or there's nothing that appears here that appears down here. That's what's going on. All right. And second proposition is that any element of Sn, in other words, any permutation, can be written as, and I'm going to hand you this notation. You might think it's sloppy to begin with, but it's totally standard, as the product of disjoint cycles. You might say, where the heck are you multiplying? Well, when I use the word product, this in this context means composition. And as we've seen already a few times, often when we're talking about general groups, I don't care if they're matrices or functions or permutations or integers, when we use the general star notation for the binary operation, typically that sort of degenerates to dot notation or the standard notation that we typically associate with multiplication. But here the quote-unquote product is inside the group Sn, so here it actually corresponds to composition. I'm certainly not asking you to multiply integers or anything like that. But we typically talk about the product of two permutations. And we mean there then whatever the appropriate group operation here, and happens to be composition. All right, I'm going to leave out the proof, but you see exactly how to proceed. If I hand you a permutation, simply tell me what all of its orbits are. For each of the orbits, construct a cycle where all the cycle does is affect whatever corresponds to the elements in each of the individual orbits. So if I know that I have an orbit in sigma that sends 1 to 2 to 4 and then back to 1, then simply do 1 to 2, 2 to 4, 4 back to 1, and leave everything else constant. If in this second orbit of the original permutation it switches 6 and 7, that's fine. Then simply write down the permutation of all of Sn that switches the two things in question, leaving everything else blank. And in that way, hey, even if you had more orbits corresponding to it, if you had 3 orbits or 10 orbits, it doesn't really matter. You'd be able to write the original permutation as a product of disjoint cycles. Okay. All right. Now things get a little bit hairier. You have to be really careful when you're reading these things. Again, this does not say that any 2 cycles commute. It only says that you're guaranteed that if the 2 cycles happen to be disjoint, then they commute. I'm not proving that for you, but intuitively that's not too bad to see, because if they're disjoint and you run it through one and then you run it through the second one, if there was an effect by the first one, then there's no effect by the second one. And whether or not you do the no effect first or the no effect second is irrelevant. Okay. This notation for permutations is a little bit cumbersome. You keep having to write out whatever the underlying set is, here 1 through 7, and then you write out what the output for each of the inputs is. But it turns out in the specific situation where I've handed you a cycle, rather than just a general permutation, in the specific situation where the entire permutation simply tells, or is simply described by telling me what happens to one element and following it through, that there's a significantly shorter notation that we can use for those types of permutations. And this is usually referred to as cycle notation. And all it is, folks, it's nothing new. It's just shorthand notation for permutations which happen to be cycles, And hey, it's sort of easy to figure out what the notation should be. Just tell me what the guts of the permutation is and just conclude or understand that if you haven't mentioned an underlying element of the set, that it doesn't get moved. So this permutation that I wrote down here, tau, the permutation that takes 1 to 2, 2 to 4, and 4 back to 1 and leaves everything else the same, we simply denote by, put a left paren, 1 to 2, 2 to 4, 4 back to 1. Just write that. So the interpretation is this permutation takes the number 1 to the number 2 to the number 4, and since I've gotten to the end of the parentheses here, the understanding is that then 4 goes back to 1. Karen, question? Oh, so the question is, can a cycle be a permutation in and of itself? Yeah, it very much can. Here is a cycle. If somebody had just dropped that in your lap and said, here's a permutation, it doesn't necessarily have to refer to anything else. It's simply, is it the case that the permutation you've written down can be completely described just by looking at what happens to one particular element of the underlying set and following it all the way through?
What would we product that with as another disjoint cycle?
Good question. How about, let's look at kappa. Well, let's see. How would we describe this cycle? And so, let's see. This notation means I've got an underlying set. Presumably, I haven't even told you what the underlying set is, but it at least is 1 through 7. Heck, it might be 1 through 10. I don't know. But whatever kappa does, it simply takes 6 to 7. Well, there's the end. Takes 7 back to 6, and everything else stays the same. That's exactly what this does. So it's simply a significantly shorter-hand notation for the original permutation, which happens to only have one orbit. And here we have sigma then is 1, 2, 4, circle, 6, 7. If you want to put the circle in, great. If not, if you just write the two things next to each other, the understanding is that you're doing function composition. So I've taken the original example sigma, and I've written it now as the product, quote unquote, or the composition of two cycles. If you like to write it in that form, that's fine. Of course, that's the same as 2, 4. Whether you need these commas or not, some books use it, some books don't. I like using them, just so that 1, 2, 4 doesn't look like 124 or 12 and 4 or something. Okay. Questions there? Comments? Question, Davey.
For clarification, would it be better to say that tau and kappa are S7?
Oh, I see. Sure. Yeah, if you wanted to write this, then that completely clarifies what the underlying set is. But if I, oh yeah, I'm sorry, go ahead. Yeah, well.
How would we write tau though as the product of disjoint cycles?
Ah, I see. Good question. Actually, that's a great question. So here the verbiage is all that's coming into play here. It's similar to, for those of you that saw the number theory course, when we say that any integer bigger than 2 is a product of primes. Yeah, well, what if you hand me a prime number? Is that a product of primes? No, it's already prime. So when we do this, when we make a statement, any element can be written as the product of disjoint cycles. Technically, the implication is or is already a cycle itself. Cycle itself. That's a good question. Again, this is just standard verbiage here, but it's the same sort of standard verbiage as the fundamental theorem of arithmetic says that any integer bigger than or equal to 2 is a product of primes. Technically, it's either prime itself or a product of primes. Here, any element of Sn is either already a cycle or it can be written as a product of disjoint cycles. In fact, technically, I haven't really included the identity element in this description either. So what I should be saying is any element of Sn is the identity, in other words, doesn't change anything, or is a cycle, or is a product of disjoint cycles. But then that just gets way too cumbersome. So, all right, that's a good question though, because the word product typically means you have to have 2 or more, and the implication is not necessarily. All right. Okay, so warning. Warning. If I simply hand you 2 cycles that aren't necessarily disjoint, they may or may not commute. So 2 cycles, not necessarily disjoint, need not commute. 2 disjoint cycles commute. And the example is, and this will be a good practice with, how about 1, 3, 4. This will be a good practice with computing what these things do. Let's see if we can run through and figure out what would happen if I take this permutation, which happens to be a cycle, and this permutation, which happens to be a cycle, and sort of run through what the effect of the cycle is, or this composition of cycles. Well, look, remember, function composition is done in the standard order. The standard order is the reverse order from what you'd expect. We always read our functions from right to left. Let's see what this function does. Well, if I plug in 1, what happens? 1 goes to 3. It's fine. But then 3 in turn, oh, nothing happens to 3 in this one, so the net effect of 1 is it goes to 3. What happens to 2? I plug in 2 into this thing, stays at 2. I then take the output, namely 2, plug it into this thing, and it becomes 1. Next, let's plug in 3 and see what happens. Plug in 3, this first function takes 3 to 4. In turn, the output value 4 stays at 4 when you run it through this function. So 3 goes to 4. And by default, I know what has to come out here because of permutation. I need to see every element at least once, so let's just make sure it does. If I plug in 4, this permutation says take 4 to 1. In turn, this second permutation says take 1 to 2, so the net effect is to take 4 to 2. Okay. On the other hand, and this again will be good practice with computing with permutations viewed as cycles. 1, 3, 4, circle 1, 2. Let's see what this thing looks like in longhand notation. Now, folks, you expect me not to be able to write down a cycle here because there's no guarantee that in the end the product or the composition of 2 cycles is another cycle. It might be or might not be. Here it wasn't. If I had the composition of these 2 cycles, these are each cycles, the composition was not a cycle. It was this thing called sigma. Let's see what happens here. We'll do this a little bit more quickly. Plug in 1. 1 goes to 2, and in turn stays at 2. So immediately I can conclude that these 2 cycles don't commute, because in this one, 1 goes to 3, and the second one, 1 goes to 2. But let's just finish up for the sake of practice. What happens to 2? 2 goes to 1, and in turn, 1 goes to 3. So the net result is 2 goes to 3. What happens to 3? Run it through the first one, nothing happens. Run it through the second one, 3 goes to 4. Let's see. What happens to 4? Run 4 through the first one, it doesn't change. In turn, run 4 through the second one, it becomes 1. Okay, so obviously these are not equal. Not equal. Okay. All right. Questions there? Comments? Karen? Not commuting is exactly what we've indicated here. I took these 2 cycles, I composed them in this order, and I got that permutation. I just reversed them here and showed that the results. Yeah. Okay. Right. Okay. Question, Lonnie?
When you did the second example showing 2 going to 3,
Mm-hmm.
why does it just stop there? How does it go 4, 1?
Well, be careful, because this particular permutation is the composition of only 2 cycles. So the function is made up as a 2-step process. Step 1, tell me what happens when you plug the given input into this. And then step 2, what happens when you run it through the second piece of the function machine. And then you're done. Okay. All right. So cycles are nice. I mean, they're obviously notationally nice. It turns out they will be nice from a computational point of view as well. The nicest types of cycles are the cycles that correspond to orbits that only have 2 elements in them. Namely, the nicest type of cycles are the ones that simply switch 2 things. That's easy. Like kappa over there is a nice one. It's just you swap 6 and 7, and that's the effect of the cycle. In some sense, if I hand you a cycle that only swaps 2 things, all I need to do is tell you what the 2 things are. I don't even need to indicate the order. You know, do you take 6 to 7 and then 7 to 6? It doesn't matter. On the other hand, if I hand you a cycle that involves more than two things, like 1, 2, and 4, if I tell you I have a cycle that involves 1, 2, and 4, I really haven't told you enough to tell you exactly what the permutation does. All right, if the cycle involves 1, 2, and 4, does 1 go to 4 or does 1 go to 2? Does 4 go to 1? But if I've only handed you a cycle that has two elements that it affects, that means I've got a swap. And those are special enough that not only do we give them a special name, we can also write down sort of a next step in this list of propositions that says not only can any cycle be written as a product of disjoint cycle, not only can any permutation be written as a product of disjoint cycles, but in fact we can go a little bit further. We're going to give up the disjoint part, but we're going to be able to conclude that every cycle is in fact a product of these very special types of cycles. And therefore that every permutation is a product of these very special types of cycles. And the definition is this. Let me do it over here so I can continue this list. Definition, transposition, that's the word, is simply a cycle that transposes two elements. A transposition is a cycle that has only two elements in its orbit. In other words, has only one non-trivial orbit, and that orbit only has two elements. For example, kappa is above. So the point is, rephrased, i.e., transposition means that you've written down a cycle that only has two things in it, so it looks like A, comma B. So here, for instance, kappa is just 6, comma 7. Or you might look at the transposition 3, comma 4, or 1, comma 6, or it doesn't really matter what two elements you have. That's what a transposition is. Here's a transposition, here's a not a transposition. Happens to be a cycle, but it's a cycle that affects 3 of the elements in the underlying set. Transposition means you only affect 2. So the question is, well, A, why are these special? And we'll see that, probably not by the end of today, but certainly next Monday. But the question is, if I hand you something that's not a transposition, is it possible to trade it in for the composition of transpositions? Or rephrased, is it possible to take permutation and not just view it as being made up of product of disjoint cycles, but actually being made up solely of just swapping things, swapping pairs of things as you go through? And the answer turns out to be yes. So the proposition is this, and it's an interesting one because it'll allow us to compute not only with cycles but with transpositions. If I hand you a cycle, the cycle A1, A2, up through, I'll call it A sub t. I don't care how many things are in the cycle, 2 things, in other words, it's a transposition, 3 things, 4 things, etc., equals the following. Let me make sure I get this right. A1, comma AT, circle, dot, 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 circle, A1, comma A3, circle, A1, comma A2. If you want, you can put another A3 in here or something. So if I hand you a cycle, I don't care how long the cycle is, what this proposition says is that you can actually view that cycle as the composition of a bunch of transpositions. So any cycle can be written as the composition of transpositions, or we'll say the product of transpositions. The key observation, though, folks, is be careful. I haven't used this word in the proposition. When I've taken this cycle and I've written it as a product of transpositions, a product of cycles of length 2, the element A1 appears in all of these, in fact. So they're manifestly not disjoint. Proof of the proposition, I won't do it for you. I'll simply run through a few of the details, though. Proof. Well, let's check out and make sure that the net result of doing this is the same as the net result of doing this. Well, let's check them out. What happens to A1? A1 goes to A2. Is that really what happens here? Well, let's see. Plug in A1 and what do you get? Well, this first thing says take A1 to A2. So far so good. And the point is A2 isn't mentioned anymore in the rest of them. So A1 goes to A2 and quits. So that's good. If you plug A1 in, A2 comes out here. If you plug A1 in, A2 comes out here. And now what happens if you plug A2 into here? A3 comes out. Cycle. What happens if you plug A2 into here? Well, in the first step it says A2 goes to A1. Yep. But then in turn A1 goes to A3. So the net result is that A2 has gone to A3 via a little, detour through A1. So it's A2 goes to A1, goes to A3, but then A3 isn't mentioned past this, so A2 goes to A3. Similarly, A3 goes to A4. How? Because A3 doesn't move here. A3 gets moved to A1. This one is A1, A4. Gets moved. So A3 goes to A4, etc. Finally, what happens to A sub t? AT, well, I don't see it, don't see it, don't see it. Oh, here I see it. AT goes to A1, and that's exactly what the cycle did. So here's the punchline. If you hand me any cycle, you can always write it as a product of transpositions. The way you do it, and here you have to be extremely careful in the order, because we're not claiming that the transpositions commute. In fact, they manifestly won't. You simply take the cycle, you take the first element, you write it as the first expression in each of the pairs, and then you simply list out the remaining elements of the cycle in reverse order. You list them out from AT back to A2. So proof, just follow each of them through. Follow each element. For example then, if I hand you, let's say this cycle that we've called tau before, example, tau is the cycle 1, 2, 4. What this proposition says is that I can actually write tau as a product of a number of transpositions. Here's how you do it. You write down the first thing. Write down the first thing. Then you write down the first thing again. Let's see how many times. Well, you need to fill in all the remaining things from the original cycle backwards in the second slots here. So 1, 4, 1, 2. Check that it works. Just, at first if you're a little bit unsure, what does this thing do? It says take 1 to 2, and then nothing happens to 2. So the net result is 1 goes to 2. Good. What happens to 2? Plug in 2. In this first step, 2 goes to 1. In the second step, 1 goes to 4, so the net result is 2 goes to 4. Good. What happens to 4? Nothing there. Plug in 4, 1 comes out. Let's do another example with a cycle we maybe haven't seen before. Let's call it gamma or something like that. Gamma is 2, 5, 1, 7, 3. Written as a product of transpositions. Can be written as, I'm going to write the number 2. How many times? However many times I have left over once I've written down 2. So I'm going to write it down 4 times. So 2, comma, 2, comma, 2, comma. And now I simply lay in the remaining elements in reverse order. 2, 3, 2, 7, 2. I don't know, slightly less computational way to phrase this proposition is every cycle can be written as a product of transpositions. Not of disjoint transpositions, but a product of transpositions. So here then is a third proposition to add to this list. Look, folks, any element of Sn can be written as a product of disjoint cycles. So if I hand you any permutation, as a first step, you can always write it as a product of cycles. In turn, each cycle can be written as a product of transpositions, although not necessarily disjoint. That's fine. So those two pieces together give any element of Sn is a product of transpositions. And again, I use this word is a product of, or this phrase is a product of, loosely in the same sense that we use it in the context of something like the fundamental theorem of calculus. I should state it as any element of Sn is either the identity or is already a transposition or is a product of transpositions. Although it's interesting because here, technically I can get by with this phrase without all those caveats. It is actually the case that every element of Sn is a product of transpositions, as long as you don't require me to write them as disjoint transpositions. The reason will be I'll be able to write the identity element actually as a product of transpositions, and I'll be able to write any transposition actually as a product of transpositions. All right. Questions? Comments? What we will do next Monday is look at some very special subgroups of Sn that correspond to the way that you write an element of Sn as a product of transpositions. And we'll look at some of the issues surrounding that next time. But what I want to do now is, all I've done is put together on one page some information that I've copied directly out of the text. If you're doing this online, I've put a copy of this sheet on the course website. You can just go and copy it off. Again, it's nothing outside of what you've already got in your text. It's just I've put all the information in one place. Specifically, what I've done here, folks, is I've written down or put together the group table for the specific group S sub 3, and this author uses some specific letters to denote the elements of S sub 3. He calls them row 0, row 1, row 2. This thing is the Greek letter rho. And mu1, mu2, mu3, that's the Greek letter mu. And then I've also listed on this sheet a group that I'll talk about for the last 5 minutes of class here, and then we'll pick up again next Monday. Folks, inside S sub n, and I'll focus on the specific case n equals 4 to start with, but this will happen and be true for any n bigger than or equal to 4. Technically bigger than or equal to 3, but it's uninteresting when n equals 3. If I hand you the number 4 and I ask, tell me all the permutations there are of the underlying set 1, 2, 3, 4, I know how many there are. There's 4 factorial or 24 of them. Okay. Well, what I'm about to do is look at a subset of those 24 permutations. I don't want you to look at all of them. The only permutations I want you to look at are those that arise in the following way. And it's sort of an interesting geometry, and this is going to sort of introduce us to this connection between group theory and geometry, which was one of the historical motivators for looking at groups. Take a square, okay? And what I want you to do is label the sides of the square in a standard order. It doesn't really matter which order. How about 1, 2, 3, 4? Label them either clockwise or counterclockwise. The issue, well, it won't be an issue, we'll put it that way. And now what I'm going to ask you to do is view this thing as a piece of cardboard where you've labeled the 4 corners. Take it out of the board. Take the piece of cardboard, flip it around any way you want. Flip it or rotate it or don't do anything to it. I don't really care. Then put it back on the board. And the question I want you to ask is, follow through what the original numbering was versus the number that it lands on. Okay. So for example, if I pick the thing up and I somehow diagonally flip it along this axis and I put it back down, then what would have happened is, let's see, the number 4 would land on the number 2, the number 2 would land on the number 4, the numbers 1 and 3 would stay the same. Here's another possibility. I pull this thing out of the board, I sort of flip it around a vertical axis, and I put it back. Let's see what that would mean. That would mean that 1 would eventually land on 2, that 2 would, well, when you flip the thing around, wind up on 1, 3 would land on 4, 4 would land on 3. In this way, what we're going to get is a permutation. As long as you're not bending or folding or, crumbling up the square, if you pick it up, flip it around, or do anything you want to it without changing its shape and then put it back down, you've affected or produced a permutation of the numbers 1 through 4. And it turns out that the collection of permutations that you get, that you can somehow view as being generated by the permutations of a square, doesn't give you all the permutations. You're not going to get 24 different ones. Intuitively, why? Because if I pick the square up, let's see, regardless of how I set it back down, the corner 1 is always going to be next to the corner 2. For instance, the corner 1's never going to be next to the corner 3, regardless of what I do to the square, because they're already at opposite corners. They've got to stay at opposite corners. So if I've told you where 1 goes, I can't put 3 next to it, because 3 isn't next to it. So the indication is that the permutations that arise this way don't reflect or correspond to all the possible permutations, only some of them. You only get a subset of the permutations. And we'll call that subset the subset of rigid rotations or rigid motion of the square. I'm not going to write that down because we're not going to use that notation here, but that's typically what this thing would be called in most textbooks. The standard letter notation for the collection of permutations that arise from motions, rigid motions of the square, is D sub 4, rigid motions or rigid motions of a square. Here's a proposition. Proposition: the permutations that arise from the rigid motions of the square give a subgroup of S4. Subgroup statement, folks. How do you prove a subgroup statement? You have one way to do it. Subgroup theorem, exactly right. What do you have to do? You have to convince me that if you take two things that correspond to rigid motions of a square and you compose them means do one then the next, that you get a rigid motion of the square. Sure. Do one, then do the next one, and what's the net result? There's a rigid motion of the square. So that was easy. There's the proof of closure. Is the identity permutation a rigid motion of the square? Sure. There it is. Okay. Don't do anything. There's a rigid motion of the square. If you have a rigid motion of the square, is its inverse a rigid motion of the square? Well, yeah, just whatever the steps were, just do them backwards. And you'll get back to where you started. So subgroup theorem. Check. Now, obviously, you can't write that out in your notes, but that's the idea. If you have something that's a rigid motion of a square, then the collection of those actually form a subgroup. And we'll go ahead and observe what the size of this subgroup is, and then we'll call it a day. Question: all right, how many ways are there of doing that? How many different ways are there of picking the square up, moving it around if you want, any way, which way you want, and putting it back down? Well, look, if I take the square and I move it around as much as I want and I put it back down, the first observation is how many different places can the corner corresponding to the number 1 land? Well, you could put the square down so that 1 is on there, or on there, or on there, or on there. So as a first step to describe all these things, there's 4 places where this corner could go. But then here's the point, folks. Once you've told me which corner you're going to put this one down on, then there's only 2 possibilities left to choose. You're either going to put this one to its right, or you would have flipped the thing over and you're going to put this one to its right. So once you've told me where you've set down the corner corresponding to the number 1, there's only 2 choices left. Actually, there's only 1 choice left, and there's only 2 choices to be made. Are you then putting things down, think clockwise, or are you putting things down counterclockwise? Have you put down the number 2 to its right, or have you put down the number 2 to its left? Okay, so how many choices or how many ways to complete the first part? 4 different ways. How many ways of determining the second piece? two different ways. You've either put the number 2 to its right or to its left. So it turns out the number of elements in this subgroup is 8. And what I have done for you is I've listed out the 8 permutations that correspond to rigid motions of the square. And in this table I've given you, well, in this second column I've given you actually the group table of these things. What we'll wind up doing is interpreting why these letters are used. For instance, he uses the rho notation. That's going to stand for rotation. The rho notation, that's going to stand for rotation. And the mu's and the deltas are going to stand for mirror images or diagonal flips, depending on what the corresponding permutation looks like. Okay. All right, this is a good place to quit. If you have any questions on your homework that you got back today, go ahead and check the web tomorrow to see whether or not the solutions are posted. Subtraction might or might not be commutative. It depends on the underlying set, meaning you can't sort of give a general description as to why subtraction isn't commutative by simply saying it's not. Show me that it's not by handing me 2 integers, 2 and 3 or 7 and 18. I don't really care, and convince me that if you do 7 minus 18, it's the same as 18 minus 7. Now, if that seems a little bit weak, I mean, a good example might be convince me that matrix multiplication is not commutative. Folks, sometimes matrix multiplication is commutative. Depends on the underlying set. Heck, if you look at those 4 matrices that we've looked at inside the 2x2 matrices over the reals, the ones with plus or minus 1 on the main diagonal and zeros everywhere else, there's a set of matrices, and multiplication on that set is commutative. So if you're going to convince me matrix multiplication isn't commutative in general, you actually have to write down some specific examples where things fail. Okay, second comment on that first homework assignment. Yeah, what some of you failed to do both in this assignment and on the second assignment was keep your eye on the prize. You're handed a set and an operation, and you're asked whether or not the set together with the operation forms a group, or maybe forms a subgroup of the given group. And in most of the situations, what you're asked to do is show that whatever it is that describes the set in question, maybe the set is the set of even numbers, maybe the set is the set of upper triangular n by n matrices having no non-zero entries on the main diagonal. Maybe the set is the collection of functions that pass through the point 1, 0 with blah, blah, blah. Whatever the set is, the prizes are always convince me that if you start with 2 things in the set and you combine them, that the result's back in the set. That's closure. Convince me that whatever the identity element is in the set. In other words, has the right property. Convince me that if you start with something in the set, i.e. has the right property, that its inverse also has the right property. And what some of you were doing was sort of either not fighting the battle at all or sort of fighting the battle. This subset that you get a subgroup of this where the operation here is multiplication. All right. Well, let's start first by looking at what the heck these things are. The elements of the set are elements of this bigger set, of this thing that you're told is a group. The things in the big set are functions. They're functions with the property that the domain of the function is the reals, what comes out is in the reals, and you're told that any function in the set has the property that regardless of what value you plug in, you never get 0 out. Okay. And then what you're asked to do is look at the subset of those things. Well, they're, again, functions with the property that when you happen to plug in the number 1, that the value 1 comes out. And so what I asked you to do as a first step here is give me some sort of pictorial representation of what the elements of this set look like. And let's see, did they actually give a name to this set, or they just said, here's a set? Okay, let's just call it S. It'll be a little. So, folks, what does it mean? What does it mean to say that you've got a function where when you plug in 1, that 1 comes out? The thing goes through 1, 1. So can you draw some pictures of some of those? Sure, here's one. That's a good one. And here's one. That's a good one. Well, I've got to make sure, though, that f of x is not 0. So I've got to make sure that whatever I draw here doesn't cross the x-axis. for what it's worth, a couple of you said, well, therefore it has to be a positive function. Well, you're not told that the functions you're interested in are continuous, simply that they're not zero. So technically, here's a valid choice. And here's an example. Goes through. There's a lot of other choices. Okay. Heck, here's one. In fact, let me put this in a little more boldly. Here's a function that goes through 1, 1. Okay, now, question, is this subset actually subgroup? Well, what do you got to do? You got to make sure that when you take two things in here and you do whatever the operation is, that you get a result that's in there. So what do you have to do? You have to take two things in there. What are the things in this set? They're functions. So you have to take two functions. What do you want to call them? How about f1 and f2? So pick two functions in the set. Show that when you do the operation, and the operation is simply function multiplication, what does it mean to be an S? It means that when you plug in 1, that you get 1 out. So how do you do that? Plug in 1. What do you get? Well, folks, what does it mean to multiply two functions together? It means you just plug it in. Definition of functions. f1 times f2. That's what it means to multiply, x squared times sine x. It means you take the x squared function, multiply it by the sine x function, and if you're handed an input, you drop it into each one, you multiply. Oh, but let's see, what does it mean to say f1 is an S? It means that that first thing is 1, and the second thing is 1, and you get 1. So look, I've plugged 1 into the product, and I got 1 out, so check, closure. I mean, I'd ask for another sentence here telling me what you just did, but that's the computation you need to do. Second, is the identity element in the subset? Well, what is the identity element? Under function multiplication, here's the identity element. I just drew it. Some of you said that the identity element is the number 1. The identity element's not the number 1. It's the function e having the property that e of x is 1 for all x. That's the identity. Because this is the function that has the property that when you combine it with any other function, it doesn't change the other function. So there's the identity function. Question, is it in the subset? It happens to be in the subset because it happens to go through the right point. Or rephrased, it happens to be in the subset because when you happen to plug in the particular input halfway, for example, this goes for both question, the even integer question, and it also goes for the upper triangular no non-zero values on the main diagonal, and it also goes for the functions question. You'll say something like, pick two things in the set. Maybe the set is the even numbers. Show that when you add them together, the result's even. Okay, that's fine. But why? Why is the sum of two even integers even? Some of you just said, well, the set is closed because the even numbers are closed. That doesn't tell me anything. Why? Because if you take two even numbers, one of them looks like 2 times x, and one of them looks like 2 times y. That's what it means to be an even number. It can write it as a multiple of 2. And if you add them together, you get 2x plus 2y, which is 2 times the quantity x plus y, which is of the correct form. It's 2 times an integer. Check. You might say, well, you're being too picky. I'm not being too picky. Heck, I mean, if the set was the set of odd integers, why is that any different than the even integers? Well, that set's not closed. Similarly, a lot of you just said, well, the identity element is in the set 2z. Yeah, it is, but why? Not that just you have to check that it is. You have to convince me that it is. Why is 0 an even number? Because you can write 0 as 2 times an integer. It happens to be that you can write 0 as 2 times 0. Why can you write the negative of an even integer as an even integer? Because negative 2 times an integer is 2 times negative that integer, which is the correct form. So keep your eye on the form. More words about that. So for example, in the second assignment, when you were asked to show that the set of n by n upper triangular matrices having no zeros on the main diagonal is a group. What some of you said was, well, if I take two things in that set and I multiply them, I get another n by n matrix. I'm done. You're not done. Okay, you get another n by n matrix. That's good. But you have to make sure that the result is in the set. You have to make sure that the result is an n by n matrix that's upper triangular, because that's what it means to be in the set, and that has no non-zero entries on the main diagonal. You have to check everything. You have to check that the identity matrix not just exists, of course it exists. You have to convince me the identity matrix is an n by n matrix that's upper triangular, that has no non-zero entries on the main diagonal. Well, yeah, it is, because it has all ones on the main diagonal and there's nothing below the main. So I'm not sure how to reinforce the necessity of, when you're showing something as a group, always looking back explicitly at what the property is that puts something in the set or in the subset, and making sure that each of the three things has the right property. Either the product of two things in the set, or the identity element of the group, or the inverse of something that's already known in the set. And I don't know, maybe you might want to just in big bold letters, here's what this set consists of. 3 properties, n by n, upper triangular, no non-zeros on the main diagonal. And then in each step, you got to convince yourself that's what's going to happen. All right. Some remarks about the function question. I think this was numbers 15 and 16 in section, was it section 4 or section 5? I forget. Number 16 and number 15. Let's look at number 16. That one was a little bit more interesting. Section 5. You're looking at this thing called f tilde is what? It's the f from the reals to the reals, where f of x not equal to 0 for all x. Right? So that's what f tilde was. And then you're looking at a subset of it. I forget what the name of the subset was. Let's just call it S. S is the elements in f tilde. G in f tilde with the property that G of 1 is 1. How did I do here? I get the number right? I think so. Okay. And the request is to show or disprove that when you look at